Hi everyone, today we're going to be showing an example of using PET thermotools to do decompression, so basically degassing of a magma ascending from depth. So as always, what you're going to do is go onto the PET thermotools, read the docs page. You're then going to scroll down to where it says, where is it? Isothermal decompression, here. So under here, you're going to click on this isothermal decompression, and then you're going to click this Python download here. This will take you to GitHub, and then you're going to click this download raw file button. That will download. If you then go back, you're going to scroll down a little bit more, and you're also going to need to grab this spreadsheet. This has the bulk composition you're going to be using. Again, press the GitHub download button there, and then put those two files somewhere in the same folder in your computer. And that's what I've done. I'm just using VS Code here as an editor. So the first cell you're going to do is basically import all of the packages you need. You need to watch the installation videos before this. If you've done that and you're doing the installation this way, this is the path to where melts is stored on my computer. So the first thing we're going to do is we're just going to run this. It also gives us the version that if you ever have a problem, you're going to want to contact Matt with or put in your paper. You then, if you're on a Mac, you're going to have to run this cell twice. If you're on Windows, you can just run it. Don't worry, it's not going to do anything because your platform is not a Mac, which is what this bit's looking for. Okay, then what you're going to do is you're going to load in this Excel spreadsheet of these compositions from the 1980 white pumice. So we'll just load this in, and you can see this is what they look like. And then we're just going to select a characteristic composition. Specifically here, this is using a water-rich inclusion. So this is actually just row 23 in the spreadsheet, or I guess 24 because Python starts from 0. So basically this is our bulk composition. It has 64 weight % silica and 6 weight % water from the melt inclusion measurements. Okay, so here's how you would run a degassing path. You're going to use this isothermal decompression calculation. And we're actually running two different calculations here, one for closed and one for open. I'm just going to start this running, so it takes about 1.5 minutes, and then we can talk through what the different variables are. Okay, so the first variable is this model variable. This is specifying that you want to use melt 1.2.0. Be careful, not all of the models in here have CO2 and water, so make sure you read the paper to check that you know which ones do. Then you're going to specify your bulk composition, so this is this white pumice that we defined up above. You're going to specify that you want to start the calculation at the liquidus, so that's through this find liquidus equals true parameter. You then are going to choose a buffer to run this at, so here this is being run at FMQ plus 2 because it's quite an oxidized system. You're then going to state the pressure in bars that you want to start your calculation at, the pressure in bars that you want to end your calculation at, and then the step size. So this will do a step every 20 bars as you decrease pressure. This fluid sat equals true parameter is quite important. What this means is if the volatile contents you give the system are higher than the amount it can actually dissolve in the system, there will be excess volatiles present at the start of the calculation. So you might have 1 volume % exsolved fluid. If this is true, it will remove those volatiles and kind of start your calculation at the point of fluid saturation by getting rid of the volatiles. If you want to start with an exsolved fluid phase to see how that changes the system, you would simply want to change this parameter to false. The other inputs are the CO2 contents, because your bulk does not have a CO2 content. Although you're using the water content from the bulk, you might want to specify the CO2. So here we're running, this is in weight percent at 0.01, 0.05 and 0.1, which corresponds to 100, 500 and 1000 ppm of CO2. We're then specifying for the closed system calculation that we do not want to fractionate fluids, so we're keeping fluids in the system as it degasses. And we also do not want to fractionate solids, so we're assuming that any microlights which are forming during degassing are sticking around. And then finally, because we're running this at 3 different CO2 contents, we've specified the label that we want our dictionary to be labelled in terms of, and I'll show you that in a second. You can see that this open system calculation is identical. The only difference is this one parameter, frac fluid. This is now going to be true. So anytime a fluid is made, it's degassed by the system. So what do these outputs look like? Let's look at the output from the closed system fractionation. So you can see this is a dictionary, and this dictionary has keys, and there is 1 key for each CO2 content you gave it. So, and you know that's the case because you asked it to label it in terms of CO2. If we take one of these keys, so we take the name of the dictionary, and then we take the name of the key. We'll see that this is also a dictionary, and it has a variety of other keys. So it has, say, the conditions you ran the calculation at, the composition of the liquids, and then there's this data frame all, which has pretty much all of the parameters you could ever want in it. So you can largely use that. But let's just show you, for example, if we wanted to look at the fluid, so this dictionary within the 500 ppm calculation, you can see that you get the water and CO2 content of the fluid and the proportion of water and CO2 in the fluid, for example. So we might want to plot up some things to look at what's happening as we degas. So what we're doing is we're just making a 3-panel subplot, and we're specifying 3 different colours for our 3 different CO2 contents. We're then going to loop through the keys of the dictionary, so just as a reminder, that is these 3 different CO2 contents, and these 3 colours that I've specified. We're then going to extract the individual calculations, so one for closed and one for open, corresponding to the key. So the first time you run through this, it's going to extract that 100 ppm calculation, and the second time it goes through the loop, that 500 ppm, and the third time it goes through the calculation, that 1000 ppm. And then what we're doing is we're taking this closed system dictionary, we're using this all key, so that gets us a data frame of pretty much every parameter we could ever want. And then on the first plot, we're going to plot the proportion of water in the fluid phase against the pressure, and do that for the closed and open system calculation. We're also going to plot the water content in the liquid against the CO2 content in the liquid. So that's your classic degassing thing you would plot onto an isobar diagram. And again, showing closed and open system differently. Now you might think so far, well, I can do this in Vesical. And you're absolutely right, you can do this in Vesical. What's different is that this allows you to interact with those phases more easily. So for example, Vesical is assuming that your composition is fixed. Here, we're actually allowing solids to form, and that is going to change the liquid composition of our system. And we can look at that here by looking at the silica content of our system. So if you run this, what you'll see is you can see to start with the proportion of water in the fluid. As expected, as you go towards shallower pressures, your system becomes more and more water dominated because your CO2 is degassing first. And you can see that on the CO2 water plot, that to start with, you're basically just degassing CO2, and then you largely degas your water after that. Now what you will see is that as you go to shallower pressures, we're starting from a composition that's about 66 weight percent silica, and we're ending up with a composition that's about 74 weight percent silica. So the question we might want to ask is, why is silica content changing? So to look at that, we're just going to look at one model, that model with 500 ppm CO2, and we're going to pull out this mass data frame. And you can see straight away, this is the mass of different things in your system. So you've got a liquid phase, you've got a fluid phase, you've got a spinel or an oxide phase, and plagioclase. So initially your system is entirely liquid with a tiny bit of fluid. And then as you go down, you can see you are forming quite significant amounts of spinel and plagioclase. So these numbers sum to 100 grams. So you're basically forming 25% approximately of plagioclase. Say you also wanted to look at the conditions in general, you could track, say, the log FO2 here. You're keeping temperature constant, so you're not changing temperature. And then you've got your other parameters you might want, like the total mass of the system and the total volume of the system here. Okay, so let's plot what these phases are doing. So again, we're going to loop through all of our dictionaries. And this time we're going to take the mass of the fluid and divide it by the total mass of the system. And that'll get us basically the percent of fluid in the system. And we're going to do that for a closed and an open system path. Then we're going to do the same for the mass of plagioclase and the mass of spinel. So let's just plot this and see what you see. So you see right away, the fluid mass, the open system has basically no fluid mass. And that's because every time you form a bit of fluid, you take it away again by definition. In contrast, you can see that if you hold that fluid around, by the time you get to the end of the calculation, you have about 6 mass percent fluid, which makes sense given the system has 6 weight percent water and the amount of CO2 is negligible. It's not even a weight percent. You can see in terms of plagioclase that you predict that you don't really form any plag, and then below about 500 bars, so 0.5 kilobars, as you're in that final stage of ascent towards the surface, that is when you begin to saturate plagioclase. And you can see Meltz predicts that a little bit earlier on you start to form your spinels, and then the amount of spinel increases at about a similar pressure, but you can see the amount of oxides is far, far less than the amount of plagioclase. We can also plot volumes instead, so there we were plotting masses. Here we're just doing the same, but we're taking the volume of the phase and dividing it by the total volume of the system to get the percent volume. And you can see this shows that, for example, in that closed system example, by the time you get to the end of your calculation, which is 50 bars, your system is almost entirely fluid. We know that when we look at these beautiful pumices that are up, so that's not a surprise. In contrast, because we keep taking the fluid away, that open system calculation isn't as meaningful of a calculation. Now you can see for that open system calculation, it predicts that by the time we get to the end of the calculation, we're about 35 volume percent plagioclase. That volume percent is far smaller in the closed system scenario because most of the volume of the system is fluids. But this is just different ways that you can look at the data. Now we saw that drastic change in silica content, and we might be interested in what that does to the viscosity. So here we're going to use thermobar, which is another Python package that I wrote, to see whether we can see how much viscosity is changing. So if you've not used thermobar before, you're just going to need to run this pip install thermobar command, and then it'll just give you the version. So again, if you have any issues, that is the thing to say in an email. So just to show you how this works, we're going to start with just calculate the viscosity for 500 ppm CO2. And we're going to do this for the closed system calculation. Let me just make sure we add that in. Okay, so basically you use this thermobar function, calculate viscosity Giordano 2008. You need to give it your liquid compositions, which is basically your dictionary for the CO2 content, and then the liquid here. You could also use all. We can change this to all. It's not going to make any difference. So that's just, again, your data frame of that single calculation at 500 ppm. You then need to give it the temperature in Celsius and convert that to Kelvin, and the water content of your system. And what that will output is the viscosity. So you can see the log viscosity and the viscosity are here. Now we might want to plot this. So again, what I'm just doing here is we're just going to be looping through all of the outputs from the decompress. And again, let's just do this for the closed system. So we're just going to make sure that this is closed. And what you will see is, and actually we might want to keep our colour. So I've not been very consistent here. So let's just put that back to colour in, and then we're just going to do zip, Helen closed colours. And then we just need to add that we want the colour to be here. So basically what this is doing is it's looping through two things now. So it's looping through the different keys in the Helens data frame closed, that's the 3 CO2 contents, and it's looping through the colours I specified in my colours. That means for each thing, it's giving it the same colour as the ways I plotted it above, just to be a bit more consistent. So I also do need to add it here. Colour equals colour. There you go, they all plot on top of each other, so it doesn't really matter. But what you can generally see is that as you decompress, your melt viscosity goes way, way, way higher by a factor of 2 on a log scale at least. And you can see that correlates pretty well with your increasing silica content, so your silica content going from 66 to 74. And you can see also we know 3 main things affect viscosity: temperature, we're holding that constant, so that's not a variable here. The melt silica content, that's how many, those interlocking bonds you have, and also the water content. Higher water contents mean lower viscosity because it breaks apart some of those silica oxygen bonds. So you can see here, that's also what we're seeing, that as we're dropping water, our viscosity is going up. So this is a bit of a double whammy from the fact you're degassing water and you're increasing melt silica content. Now, one final thing you might want to do is you might want to plot a ternary diagram of the feldspar compositions, and then you could compare them to measured microlite chemistry in your system. So again, we're going to use thermobar for this. We're using this plot feldspar classification diagram. And again, we're just going to loop through all of the keys in, say, the closed system model. And then you can tell that I just added open system. I forgot to change these all before I recorded this video. So then what we do is we first of all pull out the plagioclase. So that's just the dictionary with its key, which is the CO2 content, and then what we want for the phase, which is the plagioclase. And then we're going to put this into the calculate turn points feldspar thing from thermobar, so that will calculate the coordinates on that ternary diagram. And then finally, we're just going to plot them using this scatter plot. And you can see this is where you predict that your feldspar compositions would sit. So you could then compare those two measurements. So as always, any questions, feel free to email Matt or myself. Raise a flag on, read the docs. Anything that isn't clear, please let us know.